everyone. In this video, we are going to talk about a certain type of integrals. It's the improper integrals. And we will learn how to evaluate an improper integral. So, we often don't know this or don't realize this, that whenever we are evaluating a definite integral, say a to b fx dx, in order to use the fundamental theorem of calculus, you know how we find the antiderivative, then plug in the upper limit minus the lower limit, the fb minus fa, that's the fundamental theorem of calculus. In order to use that fundamental theorem, we actually make some assumptions that we don't even realize. We assume that the integral that we are evaluating is a proper one. So what does that mean that this integral is proper? It is proper if two things happens. One, the numbers that we are integrating, the a and the b, the lower limits, they are finite values. Like some numbers, some real numbers, which means they are not infinity. And another thing, the function is continuous inside the interval. So if these two are satisfied, then this integral is proper and we can use the fundamental theorem of calculus. But if one of them fails, guess what happens? The integral becomes improper. So improper, two things can happen, right? Two different types of improperness can happen. Either these limits are not all finite, or function is not continuous inside the interval. And if that happens, that the integral is improper, then we cannot just use fundamental theorem of calculus. All right? So we have to have a different definition, a way of evaluating improper integrals. So let's start with the first type of improperness. The first type of improperness is when you have a situation like a to infinity fx dx. So the first type means one of these, the upper limit or the lower limit, they're not all finite values. One of them is, at least one of them is infinite. It can be that both of them are infinite, okay? So this is one type. Now, what are we really trying to evaluate? Try to understand that very well. So you know what definite integral gives us, right? It's the area under the curve, okay? So what kind of area are we trying to compute here? Okay, so let's quickly try to understand this. Okay, so let's say our function is something like this. And let's say a is here. Okay, so we are trying to find the area under this function from a all the way up to infinity. So all this area I want to compute, right? All this area, it keeps on going. What do you think that area will be? Because the function keeps on going. You think that it will be infinite, but not always, okay? So that's what we have to learn. Not always this area that seems like it will be an infinite area is not always going to be infinite. You can get finite area. You will see when you do the problems. But the main thing we want to discuss here, how we're going to evaluate it, because we cannot just find the antiderivative and plug in infinity. That doesn't work. That fundamental theorem of calculus works if this was a number. So what we do is very simple. We choose some point on the right side of a. Okay, let's call it a t. Choose some point. And then let's find the area from a to t. That we can do if we choose a finite value t, okay? And then we're going to start increasing this t. We're going to make t go to here and then find a little bit more area. Then go a little bit further and find a little bit more area. So what does that mean? That process we're doing, we're letting t move that way. That means t, we are letting it go to infinity. That's a limiting process. So the definition of how to evaluate this type of improper integral for the first type of improperness is you first evaluate the area from a to some t, so replace that infinity by a t, find that part that you can use the fundamental theorem because t can be any real number, not infinity, and then in the front you're going to do a limit as t approaches infinity. Make sense? So remember, if you see an improper integral, you have to use this limit definition to solve. Even if you get correct answer and you're not using the limit definition, you are not going to get full credit from me. Okay? All right, so what else can there be? Well, it can be the negative infinity to b. The lower limit can be infinite. And then, same exact definition. So what we do is, we are going to replace that negative infinity by a t and evaluate that integral using fundamental theorem, then take a limit as this t approaches to negative infinity. And the third case that can happen is both of the limits, the upper and the lower, they're both infinite. Okay, so you're finding the area under the curve all the way from negative infinity to positive infinity. So what we do then is, we don't do two limits in one integral, we split it up. Okay, we do negative infinity to, let's say, 0, find any real number between them, let's find 0. So evaluate this integral plus 0 to infinity, evaluate this integral. So mainly what we're doing is, we are making the first one like b and the second one like a. Okay, so this one you solve like part b, this one you solve like part a, with the same definition. Now, one other thing, whenever we are discussing improper integral, like I said, sometimes the area under the curve, it could be infinity or it could be a finite value. So we use a name, okay? We say integral converges, this type of integral converges if you get a finite value as your answer. So see, you're evaluating limits, right? So if limits exist, limit may not exist. If it exists, then we say integral converges. And otherwise, if the limit does not exist, we say integral diverges. So these are the terms that we are going to start using now, and you will see later when we do series, you will use these same terms there. So always remember, converges means a finite value and diverges is infinite or no area in this particular case. Okay, so this is the first type of improper integral, and then in the next video we'll talk about the second type of improperness.